This podcast is the first one in a series which will aim to cover the Energy, Power and Climate Change Unit 8 of the IB Diploma Programme Physics course. The unit looks at renewable and non-renewable energy sources and how they impact our world, including climate change, and looks in some detail at the alternative energy sources and how we extract energy from them. In general, we can extract energy when we have a flow of heat from one place to the other. For that to happen, we need a hot reservoir and a cold reservoir. Heat will flow, and we can actually tap off some of that heat and convert it into useful work for us, normally some kind of mechanical stuff. So we need to have a flow. You can see from this diagram that we can't possibly convert all of the flow of energy into work. We need to have a flow going through the system. The equation here which relates to it is we've got QH, which is the thermal energy or heat flowing out of the hot reservoir. We've got QC, which is the thermal energy or heat flowing into the cold reservoir, and the difference between the two is the work done which we extract. So the energy flowing into the cold reservoir plus the work is equal to the energy flowing out of the hot reservoir. So as I said, heat is converted into work, but not all of it. In a cyclical process, such as a thermal power station or a car engine, it produces work every cycle, every revolution of an engine. We can't take all of the energy out. We can't convert all of the heat into work. Think about it like this. Think about kinetic energy taken from moving water, like in a hydroelectric power station. If we stop the water, if we take all of the kinetic energy out of it, the water has nowhere to go. The water has to continue flowing through the system for us to take any of the energy out of it. Same with wind power. We can't stop the wind. We have to allow the air to flow through the wind turbine to actually take some of the energy out of it. Once the heat flows into the cold place, it's no longer available to do useful work. We think of it as degraded energy. So once the heat has flowed through the system and we've taken out some of the energy and converted it into work, then we call it degraded energy. Like heat coming out of an exhaust pipe of a car, we can't do anything with it anymore. We use Sankey diagrams to actually graphically represent the flow of energy through a system. So have a look at this diagram here. A couple of things to note. It comprises of arrows. One big arrow going in, if you like, and little arrows coming out. The arrow flowing through horizontally is generally the useful energy flowing out of the system. In this case, you can see we've got 25% effective power in this internal combustion engine. These arrows peeling off down here are wasted energy, degraded energy. This is in the exhaust gases, this is in the coolant of the engine, this is friction. But in general, the width of the arrow represents the amount of energy flowing in that direction or through that part of the system. And degraded energy flows downwards, let's say. So the useful energy is represented horizontally. So that's a Sankey diagram. We use most of the world's energy resources to actually make electricity. And to do that, in general, what we have is we have coils of wire which are caused to rotate within magnetic fields. And this is part of the induced EMF course in the higher level. So the coils are made to rotate through the mechanical energy inside the magnetic fields, and electricity is produced. So we have to turn those coils. We need to use the heat or some means of turning these coils. So in terms of the energy sources available for us, we have two groups, non-renewable and renewable energy. Non-renewable, things which essentially have a limited lifespan. They will run out eventually. Coal, crude oil, natural gas, these are the fossil fuels, and nuclear fuel. So these have a limited lifespan. These fossil fuels were created millions of years ago and they're not going to regenerate. We have another group which we refer to as renewable fuels, which essentially will last forever. Hydroelectric power is flowing water, wind, solar energy, biofuels, stuff we grow and we can actually turn into fuels. Wave, the motion of the ocean, geothermal, which is the heat inside the earth, and tidal power. So we'll look at some of these in more detail later on. Most of these are with us because of the sun. The sun causes these biofuels to grow. The sun gives rise to wave motion through wind. The sun is responsible for evaporating water and placing it high up so it can flow downhill again. So the sun is responsible for most of these sources. Not so nuclear fuel. It's not responsible for nuclear fuel. It's not responsible for geothermal energy, but or tidal as well. Tidal is as a result of the moon, but it's responsible for most of the energy that we use. Now, not all energy sources were made equal, and we can categorize their richness in energy in terms of their energy density, megajoules per effective kilogram. So if we look down the chart here in increasing numbers of megajoules per kilogram, we can see that pumped stored water at 100 meters dam height, that's hydroelectric power, is definitely the lowest energy density fuel. That's why we need such huge reservoirs to generate electricity. As we then move down, we see coal here, ethanol, oil, gasoline, all in the region of 20 to 30 to 40 megajoules per kilogram. As we go up into the nuclear style, we jump up huge amounts, 1,000, 2,000 times more than the other ones. And then we're into the theoretical ones, which would be produced by nuclear fusion. Mass energy equivalence equals mc squared. We've got some huge numbers there. If we could actually solve the hydrogen fusion problem, then we have essentially endless amounts of energy for ourselves. So all the nations of the world need to generate electricity for their populace, and what they choose depends on many things: the richness of the country, the available of the energy source. And the energy density can help with those decisions. A cheap, low-cost option may turn out to be better than a high-cost, high-density fuel. For example, hydroelectric power is very low density, but once the dam is made, things are fairly cheap. On the other hand, a high energy density, oil for example, means that we have lower transport and storage costs. So currently in the world, most of the electricity is generated through coal production. We've got about 40% of the world's electricity is generated through coal. Natural gas about 20%, hydroelectric 15%, nuclear 15%, oil 5%. A lot of the oil is used for actually internal combustion rather than generating electricity. We've got combustible, renewables and waste over here. In the other renewables, this little segment here, this is an expansion. We got geothermal, we got wind, solar, very, very small chunk there. It's growing, but it's still very, very small. So we can see that these clean alternatives are really a very small percentage. We still rely heavily on the fossil fuels. If you add together the gas, the oil and the coal, we're well over 50%, 60% of the world's electricity produced by these fossil fuels, which will run out one day. So, fossil fuel power production, we make most of our electricity in that way. So here's a couple of images. This one on the right is natural gas, this one on the left is coal, both in England. Industrialization came about in the mid-1800s, and factories grew up close to large deposits of coal, so that the coal was right there. There wasn't a lot of transport costs. And this contributed to the widespread use of fossil fuels in industrialized areas. Natural gas is being used a lot more these days. It's a lot cleaner than coal. It doesn't produce as much waste gases. Transport and storage of these fossil fuels is an issue. We have coal, oil and natural gas, and clearly coal is a solid, oil is a liquid, and natural gas is a gas. So in terms of transportation, some are easier than others. Transporting liquids and gas fossil fuels is simple. Once you've built a big pipe, that is. So you build a pipe and you just pump it. It's pretty cost effective. Solid fuels like coal, you've got to use trains and ships. This is why the coal-fired power stations are normally built next to coal reserves and also next to water for cooling as well. It is, however, possible to grind the coal up into powder and pipe it over short distances with air blowing it along. Shipping oil, though, is hazardous. When you get spillages, that's pretty bad. Shipping natural gas is possible if pipes are not possible because of the increased distance. Storage of solid fuel is easier, however. You can just dump it in a big pile, whereas storage of liquid and gas requires big containers. So there are advantages and disadvantages of either in terms of storage. So the general mechanisms of generating electricity from fossil fuels is we burn the fossil fuels. We have a diagram here showing coal. We've got the pulverizer here, it's grinding the coal up, it's being burnt. That's used to heat water. The water generates steam, and the very high pressure steam turns the turbines here. The turbines are mechanically linked to the generator, which is the coils rotating the magnetic field, and we get the electricity generated. The steam is then condensed in the cooling towers back into water, and we have this closed system here. So we need a lot of water to cool the steam down, which is why power stations, thermal power stations, are built near water supplies, and that's the steam we see coming out of the big, huge chimneys. We also get pollution from the burning coal going up this way. This precipitator takes out some of the pollution, the particulates, and then we've got the gases and smoke going up here, all the greenhouse gases, the carbon dioxide and stuff. The efficiency, due to thermodynamic reasons, we have a maximum possible efficiency of only a little over 50%. Natural gas power stations are almost up to 50% in terms of efficiency, much better than coal and oil, which are stuck around 35 to 38% efficient. So natural gas is better on many fronts, more efficient and less pollution. Let's take a look at a quick question. Input and output of fossil fuel power stations. So a typical output of a fossil fuel power station is around about 500 megawatts. We got this as the power output. Efficiency of a coal-fired power station about 35%. Energy density of coal 30 megajoules per kilogram. So we can use that to calculate how many tons of coal are needed per day to run this power station. So first part, we need to work out how much energy is going into the power station. So we know that 500 megawatts is coming out, and we know the efficiency is 0.35. So divide the output by the efficiency, we get the input. So the input is of this order here, 1,429 megawatts of energy is going in. So in terms of how much coal is burnt per second, we know that the coal's energy density is 30 megajoules per kilogram. And we know the power is 1,429 megawatts, so we can just cancel the megas out if you like, forget the megas. So we're dividing 1429 by 30, and we get 47 kilograms per second of coal being burnt. We just need to scale that up now to the day, multiply by 60 to the minute, 60 to the hour, 24 to the day, and 47 kilograms. And we have 4.1 times 10 to the 6 kilos, or 4.1 times 10 to the 3 tons per day, 4,100 tons per day. Quite a lot of coal. So there are some well-known environmental issues about burning fossil fuels, which I'm sure you know about. All fossil fuels release carbon dioxide into the atmosphere when burnt, and this causes what we call the enhanced greenhouse effect, which we'll look at later on, which is the main cause of climate change. So coal releases the greatest amount. So coal is the biggest problem, although we generate most of our electricity from coal. Also, open gas mining is pretty ugly. Pit mining is very dangerous. There are many deaths annually of coal miners, especially in China. We have gas pollutants, sulfur dioxide, which can cause acid rain. So coal's rather nasty. Oil releases slightly less carbon dioxide than coal, but essentially it has the same combustion problems. Natural gas releases about half as much carbon dioxide as coal due to a more complete combustion, so there's less pollutants. Methane is a potent greenhouse gas, so if gas does spill into the atmosphere, it can enhance greenhouse effect as well, which is why we often burn off natural gas from oil fields. We sometimes see these big flames burning out the top of oil rigs. So just summarizing some of the advantages and disadvantages of fossil fuels. So advantages, we've got high energy density. The reservoirs of fuel are quite easy to find, the coal fields and oil fields, etc. Coal is very common still, but running out. Liquid or gas fossil fuels are easy to transport. Power plants are very simple technology, easy to build relatively. Petroleum is most widely used power source of vehicles, and they are easier to extract and process, hence cheaper than other forms. Disadvantages: they're common, but they are being depleted rapidly. They are going to run out. Greenhouse gases are emitted when burnt. Other gases, especially sulfur dioxide, can cause environmental issues. Extraction can also cause environmental damage, loss of life, pollution, etc. Depletion is making extraction more costly, and transport is risky due to spillage. So just a selection of some advantages and disadvantages. And finally, just to end this chapter, here's a link which you might want to go to. Google this, GCSE Bite-Sized Geography Energy, and select the first hit, BBC GCSE Bite-Sized Renewable and Non-Renewable Energy. Just take a look at the advantages and disadvantages of the other energy sources on page 1 and 2, and just take some notes, so just enhance your knowledge. So that's the end of the first podcast, and the second podcast will start looking at non-fossil fuel power generation.